Hello, everybody. My name is Zach Reynolds, and I'm a second-year MPH student at Ohio University. I'm completing my Ferguson Rice Fellowship at the CDC, and my poster is titled Enhancing Resource Utilization in Multiplex Bead Assays for Integrated Serosurveillance. Starting off, I'll give you some background. Serological surveillance uses antibody tests to estimate exposure to pathogens in a population. Multiplex bead assays, or MBAs, can be used to integrate serological surveillance for a large number of diseases, high throughput, at a lower cost. The CDC's Parasitic Diseases branch has implemented MBA-based integrated serological surveillance in countries in the Americas, Africa, Asia, and Oceania. Next, we'll move into the study rationale. A 10,000 sample serosurvey testing for 10 different antigens costs around $60,000 for beads alone. Current protocols require a minimum bead count, currently 50, per analyte per sample, or a sample will be rejected and need retesting. With some surveys needing over 30% of the samples retested, this further increases cost constraints on already stretched budgets. Cost savings related to these beads could come in two forms. One is determining the lowest initial number of beads added per assay while maintaining accuracy could greatly reduce initial reagent costs. Two is determining the lowest number of beads the machine can read and not forfeit accuracy. Could result in significant resources and time saved. Now on to our methods section. In this section, we will primarily follow a protocol for the anti-PGP3 monoclonal antibody, part A, but we will also discuss the protocol for infected human serum or a sample from an infected person, which is part B. So the first thing we did was to determine the lowest number of beads the machine can read and still get a reliable result. To do this, we ran one 96-well plate with the standard number of beads added per well using the standard protocol. For part A, we used an 8-point anti-PGP3 monoclonal antibody curve as test sample along with two standard values. For part B, we diluted a positive sample to test for infection-induced anti-PGP3 antibodies. Next, we programmed the bioplex machine to read 50, 20, 10, and 5 beads per sample. Next, to calculate accuracy for part A, we created a 5-parameter logistic curve of the log of the median fluorescence intensity, or MFI values, and then interpolated the two standards expected log MFI values from this curve. Next, for the coefficient of variation for part B, or CV, for the diluted specimen, we calculated the percent variation between the MFI of 50 beads versus 20, 10, or 5 beads. The next part was we determined if a lower number of beads can be added to the assay and still maintain a reliable result. We did this by repeating step 1 from above, but we diluted beads tenfold. Next, we repeat steps 2 and 3, but we set the bioplex to read 50 beads for the normal count and set to read 5 beads for the tenfold dilution. And next, we repeat steps 4 and 5. Okay, now we're on to the general procedure. At the top, we have the 96-well assay plate. Here we add the beads, the sample, and the rest of the necessary parts of the assay. On the bottom left here, we have a zoomed-in image of one of the wells and a representation of the beads. They are much smaller in real life. Next, after the assay would be completed, we would read the beads on the bioplex machine, which is essentially a flow cytometer. The red laser is used to identify the bead region, so we know what type of antigen the beads identify. And the green laser identifies the presence of the reporter molecule in green, which is used to identify how many antibodies there are and gives us our MFI value from before. Next, let's get on to our results. So let's look at the graphs on the left first, the ones for the anti-PGP3 monoclonal antibody. Our graph on the top is looking at the number of beads added per well, and our graph on the bottom is looking at the number of beads read by the machine. These graphs look at variation in accuracy of our interpolated values from our 5PL curve compared to their actual concentrations. The non-shaded region indicates the acceptable range for variation in accuracy, and the shaded region indicates the non-acceptable range for accuracy. Next, let's look at the graph of infected human sera or a real sample from a real person on the right. For this graph, we are looking at the coefficient of variation between 50 beads read by the machine versus 5, 10, and 20 beads read by the machine. Similarly to our other graphs, the non-shaded region is the acceptable range for the CBs, and the shaded region is the unacceptable range. So now the conclusions that we can draw from those results are that fewer beads can be read on the bioplex instrument and generate results in the acceptable range for accuracy. We can conclude that fewer beads can be added to the assay and generate results in the acceptable range for accuracy. We can conclude that there is low variation between the standard 50 bead count and lower bead counts using specimens from an infected person. We can conclude that these results show that fewer beads can be used per sample in the assay, along with accepting runs with lower bead counts. Ultimately, this can lead to significant cost savings by repeating fewer plates and using less reagent in each study. The limitations for this project include that the PGP3 monoclonal antibody used has high affinity and may not be representative of polyclonal responses of varying affinities generated during host infection. Also, preliminary data with a single operator are shown. Now, preliminary data has shown significant promise. The future plans to continue this project include repeating with additional operators to confirm the repeatability of results and to test using other antigens available on the multiplex assay, 45 at current count. Okay, that is all. Thank you for your time. I would like to acknowledge funding for PGP3 assays comes from the U.S. Agency for International Development. I would like to thank the Kennedy Krieger Institute and Keith Hudson, my KKI mentor.